All right, welcome back, folks. Chapter 6, Lesson 2. We looked at work and power last video, and today we're going to look at energy number 1. There's actually going to be 2 lessons on what we chat about in this. We're going to take baby steps. So this is the conservation of energy lesson number 1. So looking at energy, it really is the same thing as work. We'll see that in a moment. Energy is the ability to do work. So if we have an object that is able to exert a force on an object for some amount of distance, because remember from last day that work was force times distance, if we have an object that can exert a force over some distance and it's got the ability to do work, then we would say that object has energy. It can also be stored work. And we'll see an example of that in a moment, like an elastic band. You stretch the thing out, and even though it's doing nothing at the moment, if you were to like snap it at somebody, it would exert a force over some distance. So there's energy or work stored in that elastic band. So we would say it has energy. The symbol for energy is a capital E. The units are the same as work, so it's J for joules. So energy and work are really one and the same if the units are identical. And it's scalar as well. We don't have to worry about direction. 2 types of energy that we are going to introduce in this lesson. One is called potential energy, and the potential energy exists because of gravity. When we put things up in the air, we know that gravitational field strengths are going to pull things down. There's this attraction force. So gravity pulls things down, and when things fall out of the sky, they have the ability to exert force over some distance. You get plunked in the head by an apple or a baseball or something. That is doing work, right? There's energy that's being exerted on you. So the calculation for potential energy, E with a little subscript P for potential, is M times G times H. And it works great anytime we take an object with mass and we lift it up into the air. If you think about this equation in terms of work, because we said energy is the ability to do work, then M times G is simply the force acting on the object, it's the force of gravity, times D, well, we would say the distance the thing is falling is the height of the building maybe that it's on. So this equation is actually just a variation of the work equation that we saw yesterday. So potential energy, M times G times H. Easy. There is another kind of energy though. So that's that stored work, right? Or stored energy when things are up in the air, thanks to gravity. Keep in mind that if there were no gravity on this planet, there would be no potential energy. So this only exists because we have gravity. The second kind of energy is called kinetic energy. And any object that's in motion is going to have some kinetic energy. And the equation for that one is E with a little subscript K for kinetic. And it's equal to 1/2 times the object's mass times the velocity squared. And I need to point this out because students forget it all the time. And I don't know what it is about this equation. If I knew what it was, I would try to fix it. But in this equation, so often, students forget to square the velocity. I don't know why. More than any other equation. In kinematics, people don't forget to square T's. People don't forget to square R's when they're looking at forces of gravity. But people forget to square velocities in this equation over and over and over again. So I want to point that out so that when you're using this equation, 1/2 mv squared, lock that into your brain that you do have to square that velocity. Now let's look at how these 2 types of energy relate to each other in sort of different scenarios. So that goes into conservation of energy. Conservation of energy says that energy can't be created or destroyed. It simply gets transformed from one type to another. That's mainly true. It turns out that there should be a little asterisk here on the energy cannot be created. It actually turns out that we have figured out how to, maybe it's not us. We figured out how to harness the creation of energy. That's how things like atomic bombs or nuclear reactors work, is you actually take a radioactive material, you put that in there, you allow something called a chain reaction to occur, and this equation takes place, E equals mc squared. You don't have to write this in, this is just an interesting little side bit or tidbit. This equation says that mass turns into energy, and you actually do, in like a nuclear reactor, let's say you put 100 kilograms of radioactive uranium in there, and you come by some number of weeks later, maybe you only pull out 99.9 kilograms of uranium. And you sort of go, well, where did that 0.1 kilograms of uranium go? It seems to be missing. Well, it actually turned into energy. And we don't know how to make that equation go the other way. We don't know how to turn energy into mass. But we do know how with radioactive things to sometimes harness that to make small bits of mass turn into large amounts of energy. Anyways, random Jeopardy fact for you. What we're going to look at in this chapter is how energy just gets turned from one type into another. And this happens over and over and over again. There's kind of like a finite amount of energy in this universe, and it's simply just transforming between the different types at any given moment. So for example, looking at conservation of energy, let's think about Joe, safely harnessed on the top of this 40-meter tall building, and he's going to drop a 2-kilogram ball off of that building. So if we think about what that ball has initially, he's kind of just like standing there on the edge, holding the ball out over the edge of the building. We'd say initially, that ball has all potential energy. It's not moving yet, but it's like 40 meters above the ground, so there's lots of ability to do work there. And if you wanted to go calculate it, potential energy is m times g times h. You throw those numbers in your calculator, you would get 784 joules of potential energy. That's how much energy the thing could do, or sorry, how much work the thing could do when you're holding that ball up on the top of the building. And then let's say Joe drops the ball. Now, as it's falling down towards the ground, the mass and gravity aren't changing, but that height's getting smaller and smaller and smaller. So what's going to happen is when Joe drops the ball, is as it gets closer and closer to the ground, it's losing potential energy. And in fact, by the time it reaches the ground, it's lost all of that 784 joules. That potential energy is going to go all the way down to zero. But it doesn't just disappear. Those 784 joules had to go somewhere. And if you think about what the ball's doing while it falls, is it's picking up some speed. It's going faster and faster. And so it's kinetic energy, which started at zero because he's just hanging on to it initially, it's going to start to grow and grow and grow. And it turns out all 784 joules of potential energy, they go all the way down to zero, but what happens to them? They simply turn into kinetic energy. So your potential energy goes down to zero, and as that's happening, just as quickly your kinetic energy is increasing. It's kind of like at the amusement park, the whack-a-mole game, where you like whack one of the moles that pops up and it goes down, but then another one just pops out of another hole somewhere. Here it's like that potential energy, you've whacked it into the hole, and it's just connected underneath of the machine, and as the potential energy drops, that kinetic energy comes up at exactly the same rate. So that means at the ground, just before the ball hits the ground, so we're not really looking at the thing actually smacking the ground quite yet, but just before the ball hits the ground, there's no potential energy, the height is effectively zero, but all of that potential energy was transformed into kinetic energy. That's what energy does. It simply changes from one type to another. And then what's kind of cool is we could say, well, if we know the kinetic energy of the ball is 784 joules, just as it's about to strike the ground, maybe we could use that to find like the velocity. So if you plug that number into 1/2 mv squared, 1/2 times 2 mathematically, we're going to solve for v. 1/2 times 2 is just 1. Square root 784. you get a final velocity of 28 meters per second. So we're going to find that we can use conservation of energy to tackle some questions that look a little bit like kinematics. Let me show you what those look like. The conservation of energy equation, this is kind of like version 1. We're going to up the ante on this in a couple of videos. When you think about conservation of energy, I want you to think like this. You've got an mgh and a 1/2 mv squared on the left-hand side of this equation, an mgh and a 1/2 mv squared on the right-hand side of the equation. And what we're going to do is ask ourselves sort of before something happens, what kinds of energy do we have? And then the right-hand side is after something happens, what kinds of energy does the object maybe have? So here's the kind of thought process you want to go through. It's a little thought experiment. This mgh, you want to ask yourself something like this. Does the object start, because this is before something happens, does it start in the air / on a building / on a hill / in a tree? You could keep going. I'm not going to write all the potential, potential energy, all the potential places you could have it. But does the object start up in the air or on something tall? For the 1/2 mv squared, you want to ask yourself, does the object start with some velocity? Is it moving initially? And it may or may not be. If it is, then you would say it's got some kinetic energy, and if the thing is at rest, like Joe holding the ball out over the side of the building, it was at rest to start, then you wouldn't have to worry about that. Now on the other side, we ask ourselves exactly the same questions, but not does the object start in the air. We say, does the object end up in the air? Because now we're looking at after some event has happened. So does the object end up in the air / on a building / on a hill / in a tree, something like that? Have you given it potential energy at the end? Is it up in the air? And then the 1/2 mv squared, not does the object start with velocity, but does the object end up with some velocity? Is it moving at the end of the event? Like when Joe dropped the ball. It was moving just before it hit the ground. We said, hey, it's got some kinetic energy. So we're going to use this conservation of energy equation for this lesson. I've got a couple of examples for us to try. Let's give those a go. We'll scroll through that. Here we go. Example 1. We've got a 0.2 kilogram ball thrown upwards at 14.2 meters per second from ground level. What is its maximum height? Now, what I want us to do is tackle this question. You could use kinematics, but I'd like us to try it with conservation of energy, which I think you might like better. Here's what I want you to do. That conservation of energy equation that we just wrote down, I want you to write the whole thing down again for every one of these questions. And I promise this is not a make work project. Get it? Make work. We talked about work yesterday. Oh my gosh, bad physics joke, sorry. This is much easier to list the whole equation and then go through those little thought processes, the questions we just talked about, and then eliminate the terms we don't need. That's much easier than trying to cherry pick out of the question what we do have. So trust me that this time investment to write the equation down is a valuable one for you. So let's look at this ball. You are standing on the ground and you throw it. We want to know the maximum height. So when you start on the ground, right, throwing upwards from ground level, do you start in the air / on a building / on a hill? Well, we're going to say that where we throw it from is ground level. So no, you're not on a hill. You're not on a building. I know maybe you're saying, but Mr. Heinrich, the ball's not actually touching the ground when you throw it. Okay, we're not going to get super picky. We'll say that whatever height you release it from, that's height 0. Is the ball moving at the start? Is the ball moving initially? And if you look, you can say, yeah, it is. That 14.2 meters per second was how quickly it was moving when it left your hand. So it did start with some velocity. Now, after is maximum height. So when this ball is at maximum height, is it in the air / on a building / on a hill? For sure it is, right? It's going to be up in the air. And is the ball moving at maximum height? No, it's not. There's that like split second where the ball is actually not going up anymore, but it's not coming down. It's sort of frozen in the air. And if we take a step back and we look at that equation, it says that the kinetic energy that the ball had when somebody threw it quite quickly at 14.2 meters per second, that kinetic energy turned into potential energy because we threw the thing up in the air. That makes sense to me. Now, some of you might be looking at this equation and going, hey, I'm going to flex my math muscles a little bit. There's something kind of cool that's going to happen here. You will notice that mass shows up in every one of these 4 terms. That means you can actually cancel the mass out if you'd like. And I totally don't mind if you do that. I will caution you that when we revisit this equation in 2 videos, we're going to add more to this equation that doesn't include mass, and then we won't be able to cancel masses out. But for now, we might as well do that, right? If mass shows up in every one of these terms, you can actually make it disappear. And what we're left with then is pretty darn easy. 1/2 v squared equals GH. To me, that's a lot easier than kinematics. It's going to be a lot quicker. So let's plug some numbers in. That's 1/2 times 14.2 squared equals 9.8 times h. And if we throw that into the calculator, all we have to do is divide by 9.8. Looks like 10.3 meters. Maximum height of that ball. So there's example 1, conservation of energy. I don't think that's too bad at all. Let's try another. Okay, let's try this one out. We've seen a question like this in chapter 4 where we drove a tractor off of a building. Here we're going to use conservation of energy to find the speed of the tractor at impact. It's going to drive off of an 18-meter tall building with an initial velocity of 12 meters per second. So conservation of energy, we want to, oops, wrong way. We want to list the whole equation, and then we're going to cross out the stuff that we don't have. Again, I promise it's easier this way. So let's ask ourselves those questions. Does this tractor start in the air / on a building / on a hill? You bet it does. Does this tractor start with some velocity? Yeah, starts with 12 meters per second. It's actually got potential energy and kinetic energy at the start. Now, at impact, that's going to be the after side of the equation. Remember, that means just before it smacks into the ground. So when this thing is a fraction of a millimeter above the ground, does it have potential energy? Nah. It's at the ground. The height's effectively 0. But is this thing going to be moving as it slams into the ground? Oh, you bet it's going to. It's going to be probably going really fast. So there's what we have. Potential energy and kinetic energy are going to combine to give us even more kinetic energy. Here we have to cancel masses. You'll notice that we're not even given the mass of the tractor. So let's take those out of there. And now we're left with something that I don't think is too bad at all. 9.8 times 18 plus 0.5 times 12 squared equals 1/2 times v squared. We're going to solve for that velocity at impact. So 9.8 times 18 plus 0.5 times 12 squared. Don't forget to square those v's. 248.4 equals 1/2 v squared. I'm going to multiply both sides by 2 to get rid of that 1/2. 496.8, that's equal to v squared. And then we have to square root to solve for v. I'm just going to save some time and space here. 22.3 meters per second. Oop, that one a bit wonky. There you go. Last time we saw a question like this, by the way, you might recall it was a projectile. We did a 2-column VIFDAT list with horizontal and vertical information. We had to pick 2 different equations. It was much more time consuming than what we just did here. So this conservation of energy, it's kind of a second option to tackle some questions that we've seen before, but it's usually a quicker option of getting a final answer compared to what we've done in the past. So a really nice way for us to solve questions that we've seen. Let's try one more example really quickly. I'm going to be less concerned with the numbers because this video is getting long, and just more concerned with the conservation of energy equation itself. Okay, last example. Doing an egg toss. So a 64-gram egg thrown at 12.5 meters per second from the top of a 45-meter tall building. How fast is it traveling when it's only 7 meters above the ground? So let's think about what types of energy we have and don't have here. So we're throwing an egg from the top of a building. So does the egg start in the air / on a building / on a hill? Yes, it does. Does the egg start with some velocity? Yeah, somebody's up there. They throw it at 12.5 meters per second. So that's the before. Now the after, it says how fast is it going when it's 7 meters above the ground? So we're not at impact this time. So when you're 7 meters above the ground, is the egg still in the air? Does it still have potential energy? Yes, it does. And is the thing going to be moving when it's 7 meters above the ground? Well, yes, it is. So this is kind of our worst case scenario, and I say that in air quotes because it's really not that bad. The worst case scenario for one of these conservation of energy questions is to have all of the terms. Now it looks like we had our Curie helping us out. He measured this thing at 64 grams, and you might look and go, oh, I need to convert that into kilograms. Or let's just take the masses out. Make life easy. And then we can go ahead and plug in the numbers that we've got. 9.8 times 45 plus 1/2 times 12.5 squared equals 9.8 times 7 plus 1/2 e squared. And if we go ahead and do some number crunching, times 45 plus 0.5, that left-hand side is 519.125. Be a little bit careful here. We've got a 9.8 times 7. That's 68.6. We can't add that to the 1/2 e squared. They're not like terms. So we will have to subtract the 68.6 from the 519.125, which gives us 450.525. And I'm going to go ahead and multiply by 2 to get rid of the 1/2. And then square root. Hey, that's going to be close to a nice number. 30. So the velocity of this egg when it is 7 meters above the ground, 30 meters per second, flying down towards the ground. So there's conservation of energy lesson 1. Try out the practice from box number 2. Again, you can find that chapter outline in the All Resources folder on the website. It's just going to be some textbook questions. Do make sure that you do this practice. It's not going to take you very long. This is a box of homework that people usually race through pretty darn quickly. We are going to revisit this topic. We're going to see this again and sort of up the ante when we see it the next time. So do make sure that you try the box number 2 practice questions. Get a handle on, maybe I'll say, the more basic questions looking at conservation of energy, and that way when we up the ante a little bit in a few lessons, you'll be ready to go. questions about this lesson, hit me up in a Zoom meeting, fire me an email. I'd be happy to go over anything from the lesson, to go over any of those practice questions. But give those a try. Have fun looking at conservation of energy.